Good day, students. Today we will learn how to integrate this beautiful integral negative infinity to positive infinity cos x over 1 positive x squared times dx. There are actually a combination of two different functions. You might be tempted to use integration by parts because of the presence of a trigonometry function and in composition with 1 positive x squared, which if it comes to the numerator will have exponent of -1, and operating it with the integration by parts is not an easy affair. In other words, we will be just ending up going around the tree. So the best way to integrate questions of this nature is as follows. Now clearly we know cos x is an even function, and that is actually multiplied with 1 over 1 positive x squared, which is also an even function. Now because of this fact, integral, it's actually negative a to positive a. If it is of this fashion, then according to the law of integrals, integral negative a to positive a f of x dx can be written as 2 times integral 0 to a f of x dx. Now it doesn't matter whether it is negative a to positive a or whether it is negative infinity to positive infinity. The function which is even in this particular defined interval will also be even irrespective of the limits hitting negative infinity to positive infinity. So because of that fact, I can safely write integral negative infinity to infinity to be as 2 times integral 0 to infinity cos x over 1 positive x squared times dx. I hope this is clear to you. Because of the fact that cos x is even and 1 positive x squared is also even, I'm able to write it like this. So having mentioned it like that, let me define a new function. We will define a new function. Now I'm going to define the function to be as, say, sum I of t is equal to. Now when you're defining the new function, you must have in mind that the new function is able to produce the given integral for some value of t. So having got that in the corner of our mind, I'm going to rewrite the new function as cos of t x divided by 1 positive x squared times the dx. Now this will generate the integral when the value of t is equal to 1. When t is equal to 1, we will produce the integral 0 to infinity cos x divided by 1 positive x squared times dx. So this is just a side note. And that is how we define the function. So I have that in mind. Now clearly you can see that this t is actually the parameter, but the variable is x. Now on the left hand side we got the function I of t. So what I wish to do is I would like to take Laplace transform, and that would give us L of I of t. Now what is Laplace transform of the function? This is nothing but integral. Of course I need to place 0 to infinity here. That is how the function is defined. So Laplace transform of I of t is going to be 0 to infinity e raised to the power of negative s times t. Now over here I need to have the function I of t times dt. This is by definition. How do I get this? This is by definition of Laplace transforms. So having got this, I know that I of t is this. So let me replace I of t by this integral. So this is equal to integral 0 to infinity e raised to the power of negative st. In place of I of t, I am going to replace 0 to infinity cos of tx over 1 positive x squared times dx times dt, right? Now this is e raised to the power of negative st and this is x dx. So the integral is actually a function of x, but e raised to the power of negative st is independent of x. So I can safely pull this. This is just like a constant, right? It has got no impact on the integrand. So I'm pulling this inside. So if I were to pull this inside, I will have integral 0 to infinity followed by integral 0 to infinity e raised to the power of negative st cos of t x over 1 positive x squared times dx times dt. Okay, now you can clearly see that this is an integrand which is a function of x, and we have to integrate this with reference to x. But I don't want to do that. What I wish to do is I would like to change the order of integration. Change the order of integration. That is perfectly allowed. Now how are we going to do that? We need to provide a justification. Simply we cannot change the order. Right, so what justification we will have to provide? Over here we will have to use the famous theorem given by Feynman. Now what is the theorem? The theorem is as follows. If f is continuous, or let me state it, if f is a continuous function defined on R, then if we were to be given an integral of this fashion, integral a to b followed by integral c to d f of x comma y dy dx can be rewritten as integral c to d followed by integral a to b f of x comma y dx times dy. So you can clearly see the order of integration is changed. Now what allows us to change this? The main thing is the function has to be continuous. Now clearly this is a continuous function. We know that. And e raised to the power of negative st has got no impact. It will not deter the continuity of this function cos of tx over 1 positive x squared. So because this is continuous, I am going to change the order. So how am I going to change the order? I am going to rewrite this as integral. It doesn't matter. This is integral 0 to infinity. This is also integral 0 to infinity. So just place that. But what we have to do is we will have to shift this in this fashion. So cos of tx times, in fact I will have to place e raised to the power of negative st here, multiplied with dt, right? So this is one integral. This is the first integral, followed by 1 over 1 plus x squared, right? In fact, it would have been much better if I would have write it over here. So let me just write this. It's 1 over 1 positive x squared times dx. So I'm going to rewrite this one more time. So this is going to be 0 to infinity 1 over 1 positive x squared. This is one quantity. So we are not much bothered about this now, but what we are much bothered is 0 to infinity e raised to the power. Let me write this in this fashion: negative st times cos of tx times dt. This is the most important thing. Once we sort this out, everything will fall in place. So what is this? This is nothing but definition of Laplace transform of cosine function. So this is nothing but integral 0 to infinity 1 over 1 positive x squared. This is nothing but Laplace transform of cos of tx, right, times dx. Now in this case my constant is x. Have that in mind. So this is going to be equal to integral 0 to infinity 1 over 1 positive x squared. By definition of Laplace transform of cos, we will have s over s squared positive x squared times dx. So we will have to integrate this. Now how are we going to integrate this? Let me just show that to you. Now this is equal to integral 0 to infinity s over 1 positive x squared times s squared positive x squared times dx. We will have to go to a new page because of the page getting exhausted here. Now this is actually an algebraic quantity, a quadratic function in the denominator, and that makes things easy for us. Because it is quadratic, we can use partial fractions, and that too we can adopt a simpler approach, because this quadratic function has got nothing in combination with. It's just degree 2 all through. Because of that fact, I'm going to rewrite this as, let me use partial fractions. We will use, let me write that, we will use partial fractions. So that would mean I would now consider, so on the left hand side, remember on the left hand side we got L of I of t. So that is coming all through, right? We cannot lose track of that. But now we will just consider S over 1 positive x squared times x squared positive x squared, this to be equal to, we are taking it to be A over 1 positive x squared positive B over s squared positive x squared. Now you might be wondering how is it possible for me to take it. It's possible because of the fact that we just have a quadratic component in the denominator, and that allows us to split the quantity in partial fractions, that too in a linear manner. So having got this, let me flip and go to the next page. So I need to now do the partial fractions. So let us do the partial fractions. So what we got s over 1 positive x squared, I'm rewriting it, times s squared positive x squared is equal to A over 1 positive x squared positive B over s squared positive x squared. So cross multiplying, we get s is equal to A times s squared positive x squared positive B times 1 positive x squared. Now what I wish to do is I would like to take x, let x be equal to 0. If I were to take this as sum 2 in 2, so this is going to be 0, so I would get s squared times A, over here left hand side is s, so this is 0 plus B. Let me take this as sum 3. Now let x be equal to sum 1 in 2, so that would mean I would have A s squared times A positive 2 times B, over here I get s. Now s squared times A can be written as s minus B, right? So if I were to represent s squared times A, s squared times A is equal to s minus B, right? I can take this and substitute it here. So this is going to be s minus B plus A plus 2 times B. I can add these two together. This would give me A plus B, and over here I got s. So if you want to push that s, you get s minus s. So this means A plus B is equal to 0. So this would mean I got A is equal to negative B, right? So A is equal to negative B, you put it in 3. I want to put this in 3. So what happens? I get s is equal to A is equal to negative B. So s squared of negative B plus B. So this is going to be negative s squared B positive B. So if I were to take B out, this will be 1 negative s squared, right? 1 negative s squared is equal to s. So if I were to write this as s squared negative 1, let me take the negative sign out. If I were to take negative sign out, this will be s squared negative 1 is equal to s. So therefore negative B is equal to s over s squared negative 1, right? So this is the value of negative B. So therefore B is nothing but negative s divided by s squared negative 1. So this is the value of B. Now you take the value of B and substitute it in 4, right? Put this in 4. Put in equation 4. So if you have to put this in 4, negative will become positive. Therefore A value is going to be positive s over s squared negative 1. But this is what we started with, right? If we were to take this as 1, so the integral, therefore the integral is rewritten as, how do we rewrite this? This is what we have got. This is equal to Laplace transform of I of t. This is equal to s over 1 positive x squared times s squared positive x squared. This has been rewritten as A over, right? We wrote this as A over 1 positive x squared positive B over s squared positive x squared times dx. Of course the limits are 0 to infinity. Now this is equal to, I'm going to substitute the value of A over here. So that would be s over s squared negative 1 times 1 positive x squared, and the value of b is negative s over s squared negative 1 times s squared positive x squared times dx, right? All 0 to infinity. Now you can take s out, you can take s squared negative 1 out, and that would give me integral 0 to infinity dx over 1 positive x squared negative, this is going to be integral 0 to infinity dx over s squared positive x squared. Now I can take s squared out, so that will be 1 positive x over s. Of course you got the square there, there is a square there flowing through the entire component. Now what is this? This is nothing but tan inverse of x, right? So this is equal to s over s squared negative 1 tan inverse of x. The limits are 0 to infinity. Now I need to integrate this. So what I wish to do is let me show the integration for that quantity. Now let me just consider, I hope you can see this, consider integral, let this constant be out, dx over 1 positive x over s squared. Now I wish to take x over s to be equal to u. So dx, this is a constant, dx constant will be there, dx is equal to du. So dx will be equal to s times du. So this is how it will be, right? So let me go back to that pen. So this is equal to 1 over s squared, that's a constant. Now integral dx, in place of dx we will have to substitute s times du. So this is going to be s times du, 1 positive x over s is u squared. So s and s gets cancelled, giving me 1 over s. So this is nothing but integral du over 1 positive u squared. Now what is this? This is nothing but tan inverse of u. But what is my u? U is nothing but x over s. So this is 1 over s tan inverse of x over s. So this is what we have got. So I need to take this and substitute it in place of this. So this is, let me write the value. This is equal to 1 over s. I can actually place 1 over s out, and this is nothing but tan inverse of x over s. And the limits are 0 to infinity. Now if I were to place infinity, what do I get? This is going to be s over s squared negative 1. If I were to place infinity, tan inverse of infinity pi over 2 negative tan inverse of 0 is 0. But for this is 1 over s. You substitute the upper limit tan inverse of infinity, that is going to give me pi over 2. The lower limit will lead me to 0. So this is what we've got. So what I wish to do is I can take pi over 2 out. So this is going to be s over s squared negative 1 pi over 2 and 1 negative 1 over s. So if you were to take the LCM, this is going to be s minus 1 divided by s, right? There is a s here, place that. There is a pi there, pi over 2, place that. This is s squared negative 1. I'm going to write it as s minus 1 times s plus 1. So s and s can be cancelled. S minus 1 can be cancelled. So I got pi over 2 times 1 over s positive 1. So this is what I have got. Now what is on the left hand side? The left hand side is nothing but Laplace transform of I of t. But we need to get the I of t back, right? So that is the entire objective of this particular question. So if you push that thing down, we would have, I'm going to use this page here. So we will have I of t is equal to Laplace inverse of pi over 2 times 1 over s positive 1, right? Pi over Laplace inverse is a linear function. L inverse is a linear function. So you can take pi over 2 out. So you get L inverse of 1 over s positive 1. Now Laplace inverse of 1 over s positive 1 is e raised to the power of negative t. This is by definition. Times pi over 2. This is equal to I of t. As I mentioned to you, the integrand is defined for t is equal to 1. Right? We need the value of the integral for t is equal to 1. I explained to you. Because that is the reason we define the function I of t. And when t is equal to 1, you will get back the given integrand. So if t is equal to 1, I will get I of 1 is equal to pi of 2 times e raised to the power of negative 1, which is nothing but pi of 2 times e. So this is for I of 1. But we don't, I hope you got that. So let me explain one more time. We need the value of the function when t is equal to 1. So I'm substituting t is equal to 1 here. So I get e raised to the power of negative 1 times pi over 2. I push the e down. So that's going to be pi over 2 times e. But this is I. But we don't need this. What do we need this? We wanted 2 times integral 0 to infinity of cos of x over 1 positive x squared times dx. Now we have got this value, right? How did we get this value? Because for t is equal to 1. For t is equal to 1, this is the value. So now what do you need to do? You need to put this value back. So if you were to put this value back, this is equal to 2 times of pi over 2 times e, right? 2 gets cancelled, giving me pi over e units. So that is the solution for this question, pi over e units. Thank you, students. Enjoy your day.